Hi everyone, this is the Hero's Dilemma, Survival Advantages of Intention Perception in Virtual Agent Games by Amani Manashilos, George Montañez, Cynthia Hom, Kevin Ginta, and Cindy Lay. This paper is one of 3 total projects covering survival advantages of intention perception in simulated agents. Our first paper specifically discusses the advantages of target awareness. This paper, The Hero's Dilemma, focuses on intentional stance by other agents. The last paper, The Gopher's Gambit, differs from the first two and studies intention based on artifacts that have been left behind as opposed to other agents. The main goal for this project is to evaluate the benefits of intention perception, which is the ability of an agent to perceive the intentions and plans of others, in improving a software agent's survival likelihood in a simulated virtual environment. In other words, is the perceptive agent strategy the best option when considering the trade-offs and interactions of many independent factors? Our research has shown that our intention recognition algorithm in this study outperformed several other well-known algorithms. One of those algorithms was tit for tat, which was investigated in Axelrod and Hamilton's well-known prisoner's dilemma tournaments. When we account for the adversarial perspective, intention recognition algorithms can also be viewed as cooperative. It has been speculated that competition repressors such as unfavorable payoffs in prisoner dilemma type scenarios may actually contribute to cooperation. Our study evaluates the performance of various strategies with respect to survival rate and provides insight on how intention perception may lead to more cooperative outcomes where both parties survive.
To answer these questions, we developed a scenario in which we have a hero and an adversary. The hero is initially hiding from the adversary, who will attack if it discovers the presence of the hero. The hero is weaker than the adversary, and so avoiding conflict is in its best interest. However, if the hero attacks before being discovered, there is an element of surprise, which improves its odds of defeating the adversary. When faced with this decision to hide or attack, we investigate which strategies lead to the best chance of survival. We model the scenario in the style of a first-person dungeon crawl video game, and the simulation plays out in a sequence of 10 discrete time steps. In any one of these time steps, the agents can either be idle in their attack cycle or dead. For the hero, idle means still in hiding, and for the adversary, it means still searching. For both, the attack cycle is a loop in which the agent attacks every certain number of time steps. So, what might be important to consider when the hero makes his decision to stay hidden or attack? Well, for one, what is the probability that the adversary will discover the hero in the first place? This is controlled by PD, which we set to a default of 0.1. This means that every time step, the adversary has a 10% chance to discover the hero. We also need to consider the relative strengths of the hero and adversary. The probability of the hero killing the adversary is denoted PKH and has a default value of 0.5, which means on any given attack, there is a 50% chance of defeating the adversary. There is no notion of health here. Each attack either kills or fails to kill. The probability of the adversary killing the hero is denoted pKa and is set to 0.7, since in our situation the adversary is stronger. Recall that there is an element of surprise when the hero attacks before being discovered. This is pKs, which is set to 0.2. This is treated as a boost to the original probability, and so the hero would have a 0.7 chance to kill the adversary if attacking while undetected. Note that this would only apply to the first attack, as any subsequent attacks are no longer a surprise. And lastly, what is the delay between being discovered and attacked? When the adversary discovers the hero, it takes a moment to process and begin fighting. Since the hero is lying in wait with eyes on the adversary, there is potentially a window in which the hero can attack first. This idea is captured by the attack cycle mentioned on the previous slide. By default, we set the duration of the cycle to 3, which means both agents attack every 3 time steps. However, the hero attacks at the beginning of its cycle, while the adversary attacks at the end, representing how the hero is already prepared to strike. Because of all of these considerations may be important when deciding what is a good strategy for the hero, we independently vary these parameters in our simulations over a range of values. When a parameter is not being varied, we leave it at the default value indicated on the right. We test several strategies, which are defined by how the hero enters its attack cycle. The first strategy is never, where the hero never enters its attack cycle and always tries to stay hidden, even after being attacked. The next strategy is always, which enters its attack cycle at the very first time step. Then there's retaliate, a tit-for-tat strategy that enters its cycle after being attacked. And we also incorporate a random strategy, which has a 20% chance of entering its attack cycle on each time step. Second to last is our intention strategy, which takes advantage of the short window mentioned earlier and enters its cycle after the adversary enters its own cycle. This has the benefit of attacking first, but notably loses the element of surprise. This strategy involves intention perception since it requires perceiving the hero has been discovered and the adversary plans to attack. Finally, we have what we call the cautious strategy. Since the intention strategy does not attack unnecessarily, it could be viewed as more cautious. We wish to show that any benefit from the intention strategy is due to the intention perception rather than a slightly more cautious behavior, and so we create the cautious strategy as a means for comparison. The cautious strategy is very similar to the random strategy in that there is a chance to enter its attack cycle each time step, but this probability is no longer a fixed 20%. Instead, we use the empirical probability of the intention strategy attacking on each time step. Thus, the cautious strategy is just as likely to attack the adversary as the intention strategy, but has no knowledge of what the adversary is doing. This disconnects the behavior from the intention perception and strengthens our ability to conclude a benefit from intention perception. Here are a couple demonstrations of these strategies in action. First up is always, which we see attacks immediately and then eventually succeeds in killing the adversary. Note the question mark on the adversary's face to indicate that the hero does not know what it plans to do. Next is retaliate, where the hero waits until it is attacked and then retaliates and is shortly thereafter defeated. Then there's intention, in which the hero can see when it has been discovered and quickly strike.
So next we're going to go into the results of our experiment. And these line graphs are showing varied parameters where each of these parameters are the considerations that we went over a few slides ago. So each graph is generated from 50,000 simulations and includes 95% confidence intervals, but these intervals can't actually be seen since they are so close to the lines themselves. On the upper left here, we see that PD, the probability of detection, is negatively associated with hero survival rate for all strategies. We note that the intention strategy has the highest survival rate for low probabilities of detection, but as this probability increases, the always strategy starts to become more favorable. This is likely because when the adversary is likely to discover the hero, it is harder for the hero to escape undetected, so it makes more sense for the hero to adopt the always strategy and simply attack as soon as they can. On the upper right, we see that the hero survival rates of the always and random strategies increase with respect to PKS, the surprise boost given to attacks that heroes make while undetected. This makes sense from the perspective of our simulation, since never and retaliate never gain the boost because they don't initiate attacks, and intention never gains the boost since it waits until detected before attacking. So thus, we note that the intention strategy is best when PKS is low, while the always strategy starts to become more favorable as PKS increases. On the lower left, we note that as the strength of the hero's attacks increase, the hero survival rate also increases for all strategies except for never. The orange line, which represents heroes using the always strategy, has the steepest slope, which means that heroes using the always strategy benefit the most from increases in hero strength. And this makes sense since a stronger hero agent can attack with less fear of discovery since they are more likely to kill the adversary. However, we do notice that the intention line, which is the dark blue line, is better in most scenarios. The bottom middle graph shows that the intention strategy offers the highest empirical survival rate when the adversary has a high chance of killing the hero in an attack. This makes sense because as the adversary's attack strength increases, it becomes more and more favorable to remain undetected. Now the bottom right graph is quite interesting. So first we see an increase in hero survival as cycle length increases for all strategies. And then this makes sense since increased cycle lengths mean that the adversary has less time to attack. But we also see that when the cycle count is 1 or 2, the intention and retaliate lines actually overlap. And this is because with super low cycle counts, it is actually impossible for the intention strategy to attack before the adversary attacks, which makes it roughly equivalent to the retaliate strategy. So therefore, heroes using always and random do better with low cycle counts, since they can actually attack first. But once the cycle count is greater than or equal to 3, the intention strategy starts to do better than all the others. And this is probably because with larger cycle counts, the adversary must wait longer to attack once they discover the hero, which makes it easier for these heroes to escape the situation entirely undetected. So overall, we see that intention, which is the dark blue line here, does the best in most of these cases, although there are a few cases throughout these 5 graphs where always the orange line does a little bit better. So next we have some heat maps showing the effect of PKH, which is the strength of the hero's attacks, and PKA, the strength of the adversary's attacks, on survival rates. So in these graphs, PKH is on the x-axis and PKA is on the y-axis, and the first row shows hero survival rate, and the second shows adversary survival rate. And for all graphs, green indicates 100% survival and red 0%. So I'm going to start by going over some of the trends for the top row, the hero survival graphs. The first thing we might note is that the intention graph is the greenest hero survival graph, which is consistent with our findings from the previous slide, where we saw that intention did the best in most scenarios. We also might note that intention, always, and random graphs have these diagonal-looking gradients, and this indicates that the hero survival for these strategies is dependent upon both PKH and PKA. However, the intention hero does do the best for low PKH and high PKA values. In other words, values where the hero is much weaker than the adversary, likely because intention heroes don't try to start unnecessary fights against adversaries that are much stronger than them. On the other hand, hero survival graphs for both never and retaliate have a gradient that gets greener as we move downwards. And this indicates that hero survival for never and retaliate is more dependent upon the strength of the adversary than the strength of the hero. And this is very interesting because in both of these strategies, the adversary strikes first. Moving on to the adversary survival graphs, we note that the always and intention graphs have horizontal gradients that get redder as we move to the right. This indicates that the adversary survival rate for always and intention is more dependent upon the strength of the hero than the strength of the adversary. This is very interesting because for both always and intention, the heroes are the ones that strike first. So we note that the hero survival is more dependent upon the adversary's attack strength when the adversary strikes first, and the adversary's survival is more dependent upon the hero's attack strength when the hero strikes first. So in general, with these two observations, it seems that an agent's survival primarily depends on their opponent's attack strength if their opponent strikes first. These heat maps are a little bit different. Again, we have hero survival on the top row and adversary survival on the bottom, with green indicating 100% survival and red 0%. However, this time we are comparing the effects of cycle length and PK. So PK is equivalent to PKA, which is the strength of the adversary's attacks, as well as the sum of PKH and PKS, so the sum of the strength of the hero's attacks, plus the surprise boost given to heroes that attack while undetected. So essentially, PK is a metric of the overall strength of both agents. So when PK is larger, it means that both agents are stronger and vice versa. In this first row of graphs, we see that heroes using more defensive strategies, so never, retaliate, and intention, have more red in the upper left corner, which means that they do better with lower PK values. On the other hand, more offensive strategies, so always and random, have more red in the bottom left corner, which means that they do better with higher PK values. This makes sense because in the previous slide, we found that when an agent is attacked first, their survival primarily depends on their opponent's attack strength. So when PK is high, the always and random strategies, which often attack first, are more likely to kill the adversary on their first attack and survive.
Through these different probabilities, we know that the intention perception is the best strategy for the hero, and although the hero performs well with intention perception, the adversary survival rate is even higher for the always strategy than just intention. But we know that intention is the best strategy to limit attacks on both the hero and the adversary, and can almost be seen as cooperation, minimizing the overall damage in the interaction. So now we consider the cautious strategy to make sure that intention perception is the best and not due to some arbitrary attack. The cautious strategy is where the hero enters each attack cycle by chance P sub I and P sub D, which still holds as the probability of detection. The intention strategy still outperforms both random and cautious strategies. This finding was important since it shows the hero survival rate is not due to more frequently or cautious arbitrary attacks, but rather intention perception is the significant factor in the hero survival. So in conclusion, intention-aware strategy significantly increases the survival of the hero in most cases. And specifically, intention is beneficial in 3 cases. 1, when the hero's first attack is weaker than the adversary's. 2, when the hero can detect the adversary's intention and then strike first before attacked. And 3, when it's unlikely for the adversary to discover the hero. Attacking first is not always a winning strategy, especially when the hero is outmatched. It's better for the hero to attack when no other options remain. But surviving the attack depends on the strength of the opponent, so intention perception allows the hero to strike first when necessary. As I mentioned before, intention can allow for cooperation and a minimized damaged outcome for both the hero and adversary. And finally, as we tested with our random and cautious strategies, the hero does benefit the most from intention perception rather than any cautious strategy. Overall, this experiment allows us to evaluate the benefits and risks of cooperation, aggression, and intention perception. When your opponent is stronger and will strike, it's better to attack first, but only when forced to. If you're the strongest of the pair, always attacking could be a solid strategy, but might also have other negative effects. But regardless, we can learn a lot by modeling the minds of other agents and attributing their intentions, whether in a virtual world or in the real world. Thank you for listening to our presentation.